Teresa, thanks for the introduction. Thanks for having me. Again, I'm Luca Carlone. I'm associate professor at MIT. I should put the word tenure somewhere in the slide after this discussion, but next time, I guess. The plan for today is to talk a little bit about the work we've been doing on multi-robot mapping in the real world and share some of the things we learned, as well as some of the things we see as immediate opportunities for the future. I'm going to present this work. The truth is that this work has been done in collaboration with many people. I'm going to mention some of them. And the single person I want to mention is my student, Yun Cheng. He's pretty much the lead author on all the papers I'm going to present today, which is amazing, to be honest. I'm very proud of him. He's at TICRA, so if you see him, just feel free to bother him and tell him that I sent you. Okay? So Yun has been leading this. The plan for today is to share 3 lines of work we've been working on. You see here the outline. I'm going to start talking about centralized multi-robot SLAM, in particular in the context of the DARPA Subterranean Challenge. Then I'm going to jump into distributed multi-robot metric semantic mapping. And then I will conclude with more recent work about multi-robot construction of 3D scene graphs. So here, if you want to find a little bit of a pattern in the presentation I'm going to give, first of all, there is a trend in which we started a few years ago doing a lot of LiDAR-based SLAM, but we are moving towards more vision or a combination of both LiDAR and cameras. And there is also a trend in the type of representations that we are building. We started a few years ago thinking a lot about point clouds being built by multiple robots. Then we evolved into building 3D meshes of the environment instead. And now we're thinking about more advanced metric semantic representations, which are 3D scene graphs. So we'll walk you through these representations, and hopefully you will understand why we care a lot about 3D scene graphs at this point. So let me start with LAMP. I'm going to tell you in a second what LAMP stands for. But the context here is that a few years ago, I think the competition started 2018, 2019, we took part in this DARPA Subterranean Challenge. The challenge was a lot of fun, was about deploying a team of robots in caves and underground environments, and the goal for this robot was to essentially do a large-scale multi-robot SLAM experiment. So the robots had to build very accurate maps of the environment and had to find objects of interest, for example, survivors, backpacks, and so on. And again, it's a multi-robot system, so you typically would deploy from 5 to 10 robots, and they will go and build a map of these caves. This is a workshop about extreme environments. The competition was pretty hardcore in that sense. You will see a little bit of the type of caves we're testing in, very extreme environment, but also just urban environments, subway type of scenes. The competition was spanning all sorts of things. And the type of output, in this case, we're doing a lot of LiDAR-based SLAM, but essentially there's a top view of the 3D map that we built through our multi-robot SLAM system. So I'm highlighting in the subtitle JPL, just because JPL has been leading a lot of this effort. We've been contributing a lot to the SLAM system of the competition, but JPL has been taking the burden of doing a lot of the real-world testing, so kudos to them. So, extreme challenge of doing SLAM with multiple robots in these environments. Let me tell you a little bit about our contribution to this domain. I will not go into too many technical details, but I want to give the flavor of what we did. So a popular approach for SLAM with LiDAR is about doing what is called post-graph optimization. How many of you are familiar with post-graph optimization? Maybe 50%. Post-graph optimization is one of the most common approaches for SLAM. The basic idea is that you model the trajectory of the robot as a graph. So in this case, the x1, x2, and so on, there are the different poses of the robot over time. So from time 1 to time 7 in this case. And the edges represent measurements between the corresponding poses. For example, the blue edges correspond to odometry measurements between consecutive poses, and the green and red will be loop closure constraints instead. So what you do for solving this kind of problem is you try to figure out, essentially, given the edges, which are the measurements, you try to figure out what are the poses x1 to x7 in this case. And you do that by solving an optimization problem, which is trying to essentially find the poses which are matching as closely as possible the measurements you're given. So what's challenging in the subterranean environment is that you have a lot of environments that look similarly. For example, the corridor over there, in this one, visually they look similar. From the standpoint of the LiDAR, they will look even more similar. So what happens is that if you do place recognition, you will have a lot of spurious loop closures. For example, you will have a loop closure saying that X4 and X7 are the same location, but that's not true in practice. They just look similar, but they're different places. So this will create essentially outliers in the post-graph optimization problem. And the issue is that standard postgraph optimization is very sensitive to outliers. So I'm plotting 3 videos. At the bottom here, the one on the left is about optimizing the trajectory without outliers. In this case, the trajectory will iteratively converge to a nice estimate. So trust me, that's close to the ground truth. But if you start having 5 outliers over thousands of edges, thousands of measurements, the same trajectory will be heavily distorted. And if you have just 20 outliers, the trajectory is completely destroyed. Okay? So essentially, you want to be careful about these outliers because it can mess up, like, a lot, like, your SLAM estimate. So when we think about outliers, people, like in robust statistics, figured out that the right way to get robustness to outliers is instead of solving no linear least squares problem, you want to put a robust loss in front of, like, the least squares problem. That was known in the 80s, like, it's not news. The issue is that the optimization problem that you get when you put the robust loss function is very hard to solve in practice. So we spent quite a bit of time thinking about how to solve these optimization problems in a better way. And the result of that, at least one of the results of that, is an algorithm which is called graduated non-convexity. By the way, not a new algorithm. It's an algorithm that was used in a different area of computer vision back in the 90s. Essentially, we realized that this graduated non-convexity is solving the optimization problem, the robust postgraph optimization problem, in a much better way. I will not tell you the details, but I will show you just an execution of this. So what you see here on the left, there is the trajectory in green. What you don't see is that there are many outliers in red. And essentially, iteration after iteration, the graduated non-convexity will disable these outliers and will just reconstruct a much better map. Without talking too much about the details, I just want to show you how powerful these algorithms are. So in this plot, I'm showing the number of outliers or the fraction of outliers on the x-axis. So 90% of outliers means the robot is doing, like, a bunch of loop closures. 90% of them are incorrect. The vast majority of loop closures are incorrect. And on the y-axis, I'm showing the error in the trajectory estimate. So you want this to be as small as possible. So our algorithm is able to be robust and to have a small trajectory error with 90% of outliers. So you can have a very poor place recognition, but the algorithm is still doing well. And if you look at the runtime, you're paying a little bit of a price in runtime, but it's still a matter of seconds, so it's not too bad. It's not too bad in practice. So this was one of the key technical insights. This use of graduated non-convexity was one of the key technical insights behind the SLAM solution that we used for the DARPA Subterranean Challenge. And the corresponding system is something that we call LAMP, which stands for Large-Scale Autonomous Mapping and Positioning. And you can get a little bit of a sense about the performance of this approach from the few results I'm showing in this slide. The table is showing essentially for different robots and for different competition. Tunnel and urban are 2 events of the competition. You can see in the table the length of the trajectories. So this will be, like, hundreds of meters to kilometers. And you can see the AT, which is the trajectory error that you are making from your SLAM solution. So these approaches are getting an error which is a tiny fraction of the length of the trajectory. You can traverse a kilometer and make an error which is less than 1 meter. So you will have less than 0.1% error corresponding with respect to the length of the trajectory. So this was something very useful for the competition. And indeed, we ended up winning first and second place in 2 out of the 3 events of the competition. We didn't do as well in the last event. If you invite me for beers, I will tell you, like, the background story, but the SLAM system was robust overall. And the cool thing is that everything we did is pretty much open source. You can go on GitHub, you can download LAMP, and you can run it on your platforms. We use very cool platforms. So we are using a combination of Boston Dynamics as well as ASCII robots, just because these were very harsh against subterranean scenarios. And I guess on the left-hand side, you could see a little bit of the reconstruction, again, of a point cloud. These are, like, maybe 2 or 3 robots. We ended up having up to 6 or 7 robots moving at the same time for the competition. So let me tell you a little bit about the challenges of this kind of idea of centralized multi-robot mapping. In centralized multi-robot mapping, you have this idea of postgraph. You have to solve some optimization problem to figure out the trajectories of the robot. And in a centralized setup, you would collect all the measurements to a central station, let's say a very powerful computer, and you would solve for the trajectories of all the robots at the same time. Okay? So what is the problem with that? Well, in a nutshell, there are both computational problems and communication problems. On the computational side, the first issue that you have is that you will have to figure out these loop closures that you have to enforce in the postgraph optimization. Loop closures will be both loop closures within the trajectory of each robot, but will also be loop closures between two different robots. It will be done by something like, like ICP, for example. You compare the scans taken by two robots, you figure out what is the relative pose of the scan, and you enforce that as a constraint in the post-graph optimization problem. The issue is that if you have to do this ICP for thousands of scans and for 10 robots at the same time, this becomes extremely, computationally inefficient. So if you do that in a centralized way, imagine that you're sending all the data to a central station. The central station will have to do ICP, and at some point, you have to do too many ICPs for the SLAM to work in real time. So we have to do a lot of, we have to apply a lot of cleverness about pretty much prioritizing the loop closures, not to incur too much computation in the process. Moreover, if you have to do post-graph optimization for a team with multiple robots and for very long trajectories, the optimization problem will be extremely heavy to solve. Okay, so you will just incur another computational bottleneck when solving the post-graph optimization problem. And finally, communication is expensive. If you do that in a centralized way, you have to send all the data to the base station. To do that and to make that possible for the subterranean challenge, we had to buy pretty expensive communication nodes. So we had these nodes that the robots were dropping along the way to create a communication network. Each of these nodes were thousands of dollars. So it's a very expensive solution that will not scale to much larger environments. So in a nutshell, centralized solutions are great, can work out if you have maybe 3, 5, even 10 robots, but probably is not going to scale beyond this size of teams just because of computational and communication constraints. And by the way, we wrote a little bit of a longer paper describing the experience doing the subterranean challenge across all the teams participating in the challenge. We had around 10 international teams. So if you're curious about long discussions about details, about what were the key tricks to make things work, as well as open challenges, other open challenges, go and take a look at this paper. There is a good overview of the engineering that went into competing for the challenge. So we said that essentially centralized is a little bit limiting. And we also said that maybe point clouds, if you have to start sharing these point clouds around, is a lot of communication to exchange. Therefore, I want to move to the second contribution, which is a system that we call Chimera Multi, which is about instead moving to distributed multi-robot metric semantic mapping. And we're going to use vision and 3D meshes instead of using LiDAR and point cloud. Let me give a little bit of context behind the idea of metric semantic mapping. How many of you have seen Chimera before? Okay, maybe half of the room, it's worth spending 10 seconds. But over the last few years, we worked a lot on this idea of metric semantic mapping. We are not the first ones, people like Andy Davison, they pioneered really this area. But the basic idea of metric semantic mapping is that you do SLAM, essentially, but not only you reconstruct a 3D map of the environment, a geometric map of the environment, but you also want to annotate this map with semantic information. For example, Chimera, which is the system we designed back in 2018, is taking image data in input, is doing some semantic segmentation on the images, and then is solving the SLAM problem to create a 3D map, which is the one that is over here. The 3D map is a 3D mesh, so the geometry of the mesh will describe where the obstacles are, but the color of the different phases of the mesh will describe the type of object, will describe the semantics of the object. For example, I don't know, gray corresponds to the ground, yellow are the cubicles, green are the chairs, and so on. So different colors will be different semantic objects. So Chimera has a lot in it, but essentially in a nutshell is solving some SLAM problem to figure out the trajectory of the robot. And as it goes, is building a mesh reconstruction by doing voxel-based mapping and then transforming the voxels into a 3D mesh. The only thing I can spend easily the talk on Chimera, the only feature that I want to point out of Chimera, which I think is very cool, is this idea of doing post-graph and mesh optimization. So in traditional post-graph optimization, you optimize for the trajectory of the robot. But the issue is that if you have also a mesh, I cannot just optimize the trajectory of the robot, because otherwise the mesh and the trajectory will get disconnected one from the other. After a loop closure, I have to optimize both for the mesh and the trajectory of the robot to keep them consistent with each other. And we came up with this idea of doing what is called post-graph and mesh optimization, which is based on a pretty old idea from computer graphics, which is called the embedded deformation graphs. It's been used in the context of SLAM for things like elastic fusion, using different representation, surfer representations. We show that we can just easily use these and optimizing one shot both the trajectory of the robot and the mesh of the environment. So abstracting away a little bit of the technical details, here what you see is a top view reconstruction of a mesh of some environment. And what you see that the robot is going around, is visiting and is building this mesh, and then is finally coming back and doing a loop closure. And the animation is showing the effect of enforcing the loop closure on the entire mesh. Essentially, by doing this postgraph and mesh optimization, we are correcting the map to be consistent with the loop closure with a single optimization problem. And you see that the correction will propagate uniformly through the entire mesh. So it's just a way to correct the overall map in a very efficient way for large-scale meshes. And by the way, in the paper, we show some cool result in which you can formulate this as a postgraph optimization problem. So you can use things like GTSM, very established things, to solve the corresponding optimization problem. And in the results, we show that if you do this and do the deformation of the graph, you get just more accurate maps. So we started doing this with Chimera in a single robot setup, but what I want to discuss today is this idea of distributed multi-robot mapping. In this case, what we are doing is to multiply Chimera, and have Chimera run on multiple robots. So in this example, we have 3 different robots are starting in a completely unknown environment. They are collecting camera data, and they are talking with each other in order to build this 3D metric semantic mesh. So what you see here is a 3D overview of the map that is being created. That's a 3D mesh. And again, the different colors will correspond to different type of semantic objects. For example, here I think the magenta are buildings, green is grass, and then the brown is just dirt. Okay, so different type of terrains in this case, or buildings. This, by the way, is a collaboration with a bunch of people. I'm putting faces here. I think Carlos is probably in the room as well. So it's a collaboration with John Howe at MIT as well as the Army Research Lab. So how do you do this kind of distributed metric semantic mapping? I will show you a little bit of the animation of the architecture, but the basic idea is that when the robots are exploring the environment, they just run Chimera. So they do single robot mapping. But when they meet each other and then can communicate with each other, they will essentially run some distributed optimization protocol that allows correcting all the trajectories in a distributed fashion and essentially solving for the trajectories of all the robots at the same time without exchanging raw data. So the trick there is to do distributed optimization and to limit the type of data that you exchange among the robots just to save bandwidth by doing that. So let me tell you a little bit more. This is the architecture of Chimera Multi, and in particular is the architecture running on each robot. So you have to multiply the same architecture for the n robots that you have. At the top, you see the type of input data that you use. So there is just cameras, either stereo or depth, and there is an inertial measurement unit. And then each robot is doing locally just as executing Chimera. So it's doing visual inertial odometry to figure out an estimate of the odometric trajectory. And then it's doing Chimera semantics, which is building this nice colored mesh. The point where the multi-robot nature of the systems comes in the picture is in the distributed loop closure detection and the robust distributed postgraph optimization. So again, what happens is that each robot is estimating its own trajectory, but whenever there is another robot within the communication range, the 2 robots will exchange information to understand if there is a loop closure between the 2. And if there is a loop closure, they will run a distributed postgraph optimization protocol to fix, to correct their trajectories. So let's visualize maybe the 2 different, let's visualize what happens in practice. Imagine that you have 2 robots. The robots are collecting a bunch of images and are doing visual inertial odometry. They're estimating their own trajectories. Whenever they are within communication range, they will exchange bag of words vector, which are just a representation for loop closure. And imagine that, for example, the bag of words vector are matching between frames of robot alpha and robot beta. What happens is that the robots will exchange key points and other information to essentially compute a relative pose. In this case, if the bag of words vector for these 2 frames will match, the robots will exchange key points and will try to compute the relative pose within these 2 frames. And after computing the relative pose, we'll pass that information to the distributed postgraph optimization to correct the trajectory. So they will use the loop closures as in traditional SLAM to fix the trajectory that they have. So let me show you this in practice. We have, the previous video was about simulation. We have now plenty of results with the real robots. So this is an example in Medfield, Massachusetts. Here we have just 3 robots decent trajectory, like 2 or 3 kilometers of trajectories. You can see the sensor data being collected on the left by each robot, and you can see, in this case, just the trajectory estimate that each robot is building. You can see 3 different colors, which correspond to the 3 different robots. So if I replay these real quick, you can see that the robots are slowly drifting because the odometry will drift. But you can also see that whenever the robots are meeting each other, the trajectory gets corrected by this post-graph optimization process. And by the end of the day, essentially the trajectory will get better and better, and the robots will have, will have a decent trajectory estimate. In a second, you're going to see also the map reconstruction. You're going to see also the impact of doing this idea of distributed post-graph and mesh optimization. So far, I'm just showcasing the trajectories, but this is the case in which each robot is also building a local mesh around it. And again, when the robots are meeting, they're doing post-graph and mesh optimization, so they're correcting not only their trajectories, but they're correcting also the nearby meshes. So at the end of the day, the robot can build a nice, globally consistent mesh just by chatting with each other and doing some distributed optimization. So in terms of metrics here, what happens is that with this idea of distributed optimization, you can get a system that is performing as well as a centralized multi-robot system. So in the top table, I'm showing for different experiments and different robots, I'm showing the trajectory error. You can see the red box over there with the trajectory error. And there is also the trajectory length. So you see that the length are in the orders of hundreds of meters, and the errors in many cases are in the order of centimeters. Of course, if there are no loop closures, the error will be large. If there are loop closures, the error will be pretty small here. But the nice thing about doing this distributed optimization trick is that you're not exchanging raw data among the robots. You're exchanging just few bits of information. Therefore, the communication bandwidth gets much smaller, much more compatible with the constraints that you have on real systems. You pay a little bit in terms of runtime. The fact that these robots will have to alternate, some optimization protocol will take more time, but will save some communication bandwidth. So we've been testing these ideas, again, in collaboration with the Army Research Lab at scale. We have been working on this for a number of years. One of the recent things that has been presented last year at Tyros is about doing large-scale testing with up to 8 robots, half an hour type of experiments, mixed indoor and outdoor environments, and with a serious way to collect the ground truth. So we did this on campus, but the type of scenarios are fairly challenging. Featureless basements, dynamic scenes, outdoor environments, indoor environments, motion blur, pretty challenging, real-world scenes. And again, scaling this up to 8 robots and trajectories which are in the order of 8 kilometers overall, so fairly long trajectories. And we released this data set. We also tested Chimera Multi, which is the system I was describing before, on this data set. And these are some of the results in which I'm showing the trajectory estimates from our system overlaid on the ground truth map that we have to build for benchmarking. And again, this is open source. At this point, if you want to go and try it out, you just have to go to GitHub. So it seems that with distributed optimization, we got a huge step forward, right? We do not need a powerful central station. We can just do distributed optimization and run these on a much larger team. So there are a bunch of positive things. The truth is that by doing a lot of experiments, we discovered a lot of trade-offs between doing distributed mapping and centralized mapping. And I'm trying to summarize some of these in this slide, but there is much more wisdom, to be honest, in the Aeros paper. The first thing that pays off if you're doing distributed multi-robot systems is on the front-end side. The front end is the one figuring out loop closures, is the one figuring out the odometry part. Essentially, when you have a distributed system, the loop closures do not have to be computed at a central station, but the robots can compute them locally, okay? So if you have 10 robots, now you have 10 robots computing loop closures instead of a single central computer doing loop closures for the entire team. So this means that it's much faster to do loop closure, and in the plot, I'm showing over time the number of loop closures that you can process. And there is a clear winner in which the distributed optimization is delegating the loop closure computation to the different robots and can figure out many more loop closures compared to the centralized, which again is limited in terms of computation. So that's the good news. Distributed is great for the front end. The bad news comes when you talk about the post-graph optimization or the back end of SLAM. So for the system we had, first of all, here I'm showing first 3 rows is about the distributed version of the system, and the last is about centralized. So the first thing that you realize is in terms of errors, these two are quite similar, actually. We don't lose much. By doing distributed multi-robot mapping, we don't lose much. The price that we pay is that the robots will have to keep chatting with each other to do distributed optimization, and the time will get from a few seconds to hundreds of seconds. So the system ends up being much slower because of that. So front end is better, back end seems to be much slower with the distributed system. And in the paper, we'll put also some more evaluation about the fact that the system is robust to drop, package drops, and a bunch of real-world conditions. I'm not going to talk about that, but feel free to look at the Aeros paper if you're curious about that. So I have around 5 minutes to go. I want to move to the last topic of today, which is about moving from 3D meshes and metric semantic SLAM to this idea of 3D scene graphs. Okay? How many of you know what a 3D scene graph is? It's always half of the room, I guess, always the same people, raising the hand. Okay. Let me tell you about, what is a 3D scene graph and why we're excited about that. The basic idea, first of all, a 3D scene graph is just a hierarchical map representation. So a 3D scene graph is hierarchical representation where at the bottom you have some dense metric information, for example, a 3D mesh. But as you go up in the hierarchy, you're abstracting away the dense information into objects, agents, rooms, buildings, and so on. So the more you go up, the more you abstract away information, the more you become a purely semantic representation. So here, all the layers are pretty intuitive. Objects and agents, we understand what they are. Rooms, buildings, we understand what they are. Places are just a topological map of the free space. So places is just a graph telling where the robot can go. And structures will be walls, ceiling, and so on. So why do we think that this representation is pretty powerful? The basic idea is that we want robots to have high level of autonomy. We want robots to be clever and to be able to execute complex instructions from humans. For example, I would like to tell the robot, robot, go search for survivors near the fridge in the kitchen. And in order to execute this instruction, the robot will need to know what are survivors, we need to know about the kitchen, we need to know about the fridge, and we need to be able to reason over relations between different things. What does it mean for the fridge to be within the kitchen, for example? And we just think that this representation is perfect because essentially it captures semantics beyond objects. Not only we have objects, we have rooms and so on, but also is a graph representation. So you can represent, through the edges in this graph, you can represent relations and say, for example, that an object is in room 7, or you can represent the fact that 2 rooms are nearby, for example. Spend a lot of time proving properties of this representation. If you're interested, you can look at our IGRR paper. This is IGRR now. But essentially, we prove that if you organize information hierarchically, you gain a lot of efficiency. You can do much more efficient inference if you organize things hierarchically instead of doing just traditional meshes or voxel-based mapping. So not only we studied and we proposed this representation of 3D scene graphs. By the way, other people Iro Armeni at Stanford has been doing a lot of pioneering. It was probably the first to propose this representation. A lot of work we did not only was to study the representation, but to come up with the first algorithms that can build these 3D scene graphs in real time. Our algorithm, or our system, is called Hydra. So imagine that the robot is starting in a completely unknown environment, and you see the camera streams on the top left. What Hydra is doing is figuring out the trajectory of the robot, is building a 3D mesh, as we described before. We figure out that there are different objects in the environment. For example, there are appliances, sink, and so on. And depending on the type of objects, we'll conclude that if there is a fridge, there is a sink, there are appliances, most likely the room is a kitchen rather than a bedroom. So we'll reason and we'll build the hierarchy as it goes in real time. So connected to the topic of this workshop, we also had an extension which was presented last year at Aeros, which is called Hydra Multi. Now you see the pattern of the naming, I guess. The basic idea here is that you have multiple robots, robot 1 to 3 in this case, or 0 to 2. Each robot is building a scene graph, and then in this case is a centralized system which are sending information to the base station, and the base station is collecting together the maps to build a unified scene graph. A couple of things that I want to mention. Again, there are a lot of details in the paper, but maybe a couple of interesting things is that once you have hierarchical information, you can do much better loop closures. For example, you can use the information that you're in the kitchen to improve the fact that you want to do loop closure with another location that was in the kitchen. So in a nutshell, what we do is to come up with hierarchical descriptors for place recognition, and we show that that improves the quality of the place recognition. And also we generalize this idea of doing post-graph and mesh optimization, which is deforming the trajectory and the mesh, to the idea of doing scene graph optimization, in which we deform all the layers of the scene graph in a single optimization problem. We show these before, the one before was simulated experiments. These real world experiments, fairly large scale. We also show that, going back to the topic of this workshop, you can do this with heterogeneous robots. You can have a robot which is just LiDAR, a robot which has camera. So the two maps will look quite different. One maybe will not have semantics, but you can still fuse them together in a single scene graph. You can still use Hydra multi to do that. I think I'm pretty much out of time, so we'll flash just one last slide. There are many things I'm excited about, and that we're doing, which are a little bit newer. I will flash just this one, which is this idea of extending 3D scene graphs to outdoor environments. Turns out that extending to outdoor environments is non-trivial. In indoor, you have a clear hierarchy of objects, rooms, buildings, and so on. In outdoors, you have to figure out what is the right hierarchy of concepts. And we have a nice way to use large language models, actually, to figure out what is the right set of concepts that you have to put in the map. The other challenge in outdoor environments is that you do not have a lot of data. You have a lot of data sets which are curated for indoor environments. It's not immediate to use outdoor environments, outdoor data sets to train these kind of approaches. So we use a tool from learning which is called logic tensor networks to improve the construction of the semantic map. So here what you see is that the robot is going around in a completely unknown environment, is figuring out objects, for example, chairs, trees, and so on. And then is reasoning over the object to figure out that there are different regions in the environment. For example, there is a road. You can see the regions. Maybe I can adjust in this part of the video. The different regions will be at the top. There is a road, off-road area. So that's the top part of the scene graph. And I think I'm out of time, so I will just conclude at this point just with a summary of the things I hopefully covered today. The first thing that we realized over the years is that representations are important. And there is a clear trend, at least in the work we are doing, there is a clear trend from purely geometric representations as point clouds to more advanced representations such as meshes, metric semantic meshes and 3D scene graphs, which are very useful to execute many tasks. There are now papers doing task and motion planning on this representation. There are papers doing human-robot interaction. But also with the work we have done, we have shown essentially that it's possible to be these representations in real time on a robot. We're very excited now about this idea of building task-driven representation. We would like for you to specify the task that the robot has to complete, and we would like for the robot to build the right map for the specific task. We have a recent paper on that, which is called Clio. Look it up on arXiv if you want. I didn't have time to talk about it. The second point is about robustness. If you're clever about doing robust estimation with tools like gradual non-convexity, you can get systems which are way more robust to bad loop closures or things like that. But there is much more to be done, in particular, just to operate in highly dynamic environments. And if you look at the paper on the DARPA Subterranean Challenge, you see that these systems still require a lot of manual tuning, which is undesirable. We would like to have some automatic tuning. Distributed versus centralized, there are pros and cons. So maybe we'll have to figure out some hybrid approach, which is getting the best of both worlds. And then we have been showing that you can do a lot of real-world demonstrations in subterranean, large indoor-outdoor environments. But there are also a lot of new opportunities, in particular when it comes to foundation models, open set semantics, and so on. And just that, when you end up doing a lot of also this field robotics work, you end up working with many amazing people. So that's an extremely fun part of the job that I just want to mention to conclude. That's all I have. So thank you for your attention. And,
Thanks, Luca. We have time for one, max 2 questions.
Sorry.
Hello.
You look familiar.
Yes, maybe. Thank you for the amazing presentation. I'm actually curious about Chimera Multi's adaptability for not only loop closure constraints, but actually more locally consistent constraint passing between motors, between robots in distributed systems, because each robot now is expected to have a local consistent estimation. Did researchers actually experiment on this? For
and the question is about global consistency for the trajectory estimated, but can you give more information?
So right now in Camera Multi you showed that the loop closure constraints actually enables a global consistent trajectory.
Yeah.
And actually this data passing for the distributed robotics, did you also experiment passing local constraints between robots to complement each other on cases that one robot solved and the other one didn't solve?
And you're concerned about maybe improving, maybe robots with heterogeneous capabilities, and maybe you want
Yes.
to, by local constraints, you mean like more improving the odometry type of thing?
Exactly. So local odometry or the features such as walls and surfaces and so on.
We didn't think too much about that. There's a lot you can do there, and in particular, if you start being aware of the uncertainty and the capabilities of the different robots, you can do a much better job at fusing things in a way that will help more the robots which are weak in terms of sensing and so on, and maybe less the robots which are strong. We didn't think too much about exchanging low-level information. There's a clear trade-off there in which if you start exchanging low-level information, the communication bandwidth will take a hit. Yeah, we didn't think too much about that.
We have one more question.
Okay.
Yep.
Thank you for your presentation. And just one simple question. Why did you choose to pass to a map representation with meshes instead of point cloud? It's only for human understandability, or is there other reasons?
Yeah, so by the way, the choice about the right representation right now, is really a bet, in the sense that there are newer representations, Gaussian splatting, nerves and so on. So really depends which representation, there are very powerful representations right now you can choose from. The reason why we went from point clouds to meshes is that first of all, meshes are more informative. You catch the topology of the environment, which is where you can traverse or not. But also you save a lot of bandwidth, right? You save a lot of memory, because instead of storing, imagine for a plane, instead of storing millions of points, you just, you have two triangles and that's it. So you can do a lot of compression by storing meshes instead. The downside of meshes is that because of the noise in the sensor and so on, they don't look as good at something like Gaussian splatting. We are trying to see if there is a representation that can be a little bit more photorealistic, but still preserve a lot of the nice properties of meshes. Good question. Yeah.
Thanks, Luca. Thanks for the great talk.